Cool. Well, welcome to Engineering 250. So, this is digital logic. It's usually the sequel to Engineering or Computer Science 120. And I'm pretty sure everybody who's here is supposed to be here because otherwise you have no access to the Zoom info. So, nobody has to get up and walk out in the beginning. All right, so my name's Nick. I've been teaching here at Clark for about a decade now, and I teach this course usually every spring. I mostly teach the 200 level computer science sequence, but I teach this course in spring and Engineering 270 in summer. So so you may see me in future courses, and if you're computer science, you'll definitely see me probably next year. So let me start off by just kind of doing the syllabus walkthrough and go through a few administrative details, and then we're going to jump right into talking about digital logic. And I want to actually get you going on your first lab today because I've scheduled that with a due date of Friday. I want to make sure people get started on the lab work right away because we're online, which means we're doing our labs using Tinkercad. So in engineering or computer science 120, how were you doing the labs where you had to build circuits and stuff? Was that using Tinkercad also?
Using Tinkercad, and it was self-discovery board.
Okay, cool. All right, so this will be somewhat familiar and hopefully comfortable. So let me go over some of the administrative stuff first of all. So be sure to read this. I'm thinking people already have looked at this. So everybody has Canvas access. So just to highlight, right? This is not technically an online class. It's considered a remote class. So online classes, materials posted on Canvas, you can kind of like go through it at your own pace. If it's a hybrid class, there may be some scheduled meetings and so on, but it's kind of a do it at your own pace and your own way kind of thing. That's not what this course is, okay? This is considered a remote course, which means we meet every Tuesday, Thursday, 12 o'clock. And it's like a regular classroom. It's structured like a regular face-to-face class, except instead of being face-to-face, we're remote through Zoom. But so just want to be clear on that. I put a little note on here just to give you something to think about. I'm gonna ask you to try and stay present as much as possible during class. Now, this is a long class. It's an hour and 50 minutes, okay? And we'll usually take a break somewhere partway through. But, even in my 50-minute classes, it's a challenge to sort of stay present with what we're doing in class for that time. It's hard when we're face-to-face, especially if you've got a laptop or a phone in front of you. It's easy to surf. It's easy to, think about, things you need to be doing for other classes and so on. And we drift. And everybody does this. I do this when I'm pulled into administrative meetings and it's a Zoom meeting. Yeah, I'm folding laundry, I'm doing dishes, I'm making food, I'm grading papers, and I'm listening in the background, right? That's natural, it happens, but as much as you can try to avoid that, it's going to help you with this course, right? Because what's going to happen is you're going to drift away and be doing some other things because what we're talking about seems familiar and obvious. And then at some point you'll check back in and you won't know what we're talking about. And you'll try to make sense out of it and you'll say, well, I'll just watch the video later because I record these classes and post them. And that can work once in a while, but it's too easy to find yourself, the day before an assignment's due with 7 hours of videos to watch to try to catch up. And so of course we fast forward through those and we skip around and we try to get what we can, and it's a really uncomfortable way to try to learn the material. And this course in particular, there's a lot of material, right? We start off with kind of a rehash of what we did in ECS 120, when we talked about digital logic, but we go so far beyond that, and we go really fast. So as much as you can kind of stay present during the class time, I'd invite you to do that. And if you find yourself drifting, just bring yourself back, right? And if you find that you're lost, it's okay to say that, right? To just say, I'm not really sure what that means, right? Or can you go back and review that again or something like that? And I guarantee you, if you drifted off and you came back 5 minutes later and you're not sure what we're talking about, there are going to be other people in the class in exactly the same situation, right? So you're not only doing yourself a favor, but you're helping other people, and it's absolutely not a problem. I can sit here and I can talk, for 25 hours about digital logic without a break probably, and just keep going on and on and on. That's not going to do anybody any good, right? The goal here is not for me to practice talking about digital logic. The goal is for you to learn about digital logic. And so, if we're going too fast, if we're going too slow, if I missed something, or if you missed something, right, it's important that we go back and try to make sure that this is making sense as we go. So I'd like this to be as interactive as possible. I'm not requiring people to put on their cameras, but if you want to put on your camera, I think it will help you with staying, in the mindset of being in class. It will also help you, to some degree connect with other people and feel like you're doing more than just sitting in another Zoom session staring at your computer, when it's this beautiful sunny day outside and you got physics work to do or whatever. So that's a possibility also. All right, so we meet on Zoom. You've got the Zoom code because you're here. If this code changes, I'll do a Canvas announcement, okay, to let you know what the new Zoom link is, which brings up the point. Make sure that you've set up Canvas to notify you of, announcements, changes to assignments, things like that. Canvas will let you dial in, how often you want announcements, do you want them pushed, and so on and so forth. I recommend setting up immediate announcements. Weekly digests are great unless, it's something like, oh, your exam has changed from this date to that date, right? You don't want to wait till Sunday to hear about that. So set up Canvas to let you know right away, and I'll use that as kind of an emergency notification for anything I need to tell you about. All right, so that's to be sure to read this. Syllabus you may have looked at already. So digital logic, 5 credits. You've got the prerequisites if you're here Tuesdays, Thursdays, 12 to 1:50. My name's Nick again. Absolute best way to reach me is nmacias@clark.edu. Okay, that's my direct email. That works much better than trying to reach me through Canvas. Okay, Canvas email has not always been the most reliable. So do nmacias@clark.edu if you want to be sure to reach me. My office hours are posted on ENGR250.com/schedule. So my general office hours are daily 8:45 to 9:45. Okay, and you can come by those. You're competing with people from other classes. You're competing with people looking for advising. I also have 3 hours set aside just for this class, and that's Tuesday, Wednesday, Thursday from 11 to 12. Okay, and those are not posted on this website. Those are just for this class, Engineering 250. So you can come by during those times and, talk about class, work on the lab, or, advising or whatever else. But I'm reserving those just for 250. So Tuesday, Wednesday, Thursday, 11 to 12. So right before class, Tuesday, Thursday, and then the same time on Wednesday. You can work on the labs, obviously, any time that you like, especially since they're being done online. But if you want help with your labs, that's a good time to find me, and we can screen share, and I can look at what you're doing and give you suggestions and so on and so forth. I'll let you read the course outcomes on your own. These will make more sense probably as we go further through the course, but these are the things that you are supposed to come away from the course knowing. And having passed the class with a C or better, we're basically saying these are the things that you now know and can do. And that works as far as, you know, being a prerequisite for other courses and also being accepted as equivalent to what you would need at a university, typically WSU, to be able to take their courses. This is a rough shot at a tentative outline. It's probably meaningful today, but beyond that, who knows? It kind of depends how the things go. Sometimes we speed up, sometimes we slow down, but just to give you a kind of idea of the things we're going to be covering, although possibly not, you know, in that exact schedule. Grading for the course. So pretty straightforward assessment. You'll have 7 labs for a total of 25%. You'll have weekly homeworks, which you'll turn in online for a total of 20%. And then a midterm 25, comprehensive final 30. Okay, so pretty straightforward. And you can see letter grade assignments on the engineering computer science webpage. I'm not going to go through this. I read through some of this in detail for my 101 class, but hopefully everybody has, you know, been taking classes and has at least looked at these once, which is, you know, questions of academic honesty and plagiarism, computer misuse, and so on. The main thing I'll say about this, make absolutely sure that the work you're turning in is your own work, okay? Stay as far away as you can from places like Chegg, right? It can arguably be useful to see solutions to problems to help you understand, but we're going to go through lots of examples in class. The homework sets always have a solved set and an unsolved set, and the solved set has questions similar to the unsolved ones, so you can see samples in there. And if you start going to you know, sites like Chegg to look at solutions to problems, it's really hard sometimes, you know, if you've seen a solution to a problem you're trying to turn in, it's really hard to unsee that. And then, you know, actually write a solution that is your own. And that can be a problem. So I had 2 students Chegg out of the sequence last year, one in 250, one in 270, and I've had 3 students in the CS classes get into trouble this year so far. It's a big problem, and it, you know, most people don't start off saying I'm gonna cheat, you know, I'm gonna get someone else to do my work. But it's a really fine line between, you know, looking at something that tells you, you know, how to do something to, you know, actually having somebody else do it and have that be what you turn in. So we take it pretty seriously. And if you have any questions about that, right, just come and talk to me. There's a lot of fantastic resources available online, and you know, I'm not going to say don't look at anything online. Just be careful that you know where that line is, and if you think that, you know, you might be crossing it or something, send me an email, come by office, we can talk about it. Support services if you're in a situation where you think some kind of accommodation would be helpful to you, whether it's extended testing time, low distraction environment's not really an issue since we're online, but you know, having a note taker or, you know, things like that, talk to me or talk to the DSS services, DSS office, and there's contact information in here. Make sure you read and understand the non-discrimination policy. The one-line synopsis of all of this is treat people well, right? Treat people the way you want to be treated. We're adults, and we're all here to learn, and we don't want to interfere with other people's learning. All right, so you can read through the rest of this. If you have any questions about any of this or anything else, just or if you have questions in class, feel free to either use your microphone and say, "Hey, I've got a question," or hop into chat. And I keep a chat window up so I can see if you ping me in there and so on.
I have a quick question.
Yeah.
So do you record your Zoom meetings at all?
Yeah, so this class is being recorded, and I post the videos on YouTube. I don't display any individual information, so the chat window, the list of participants will not be recorded. What I'm recording is exactly what you're seeing here in this shared screen, which right now, is my picture and a web page. So the only possible privacy concern I can envision is if somebody's concerned about their voice being recorded, right? If you use your microphone, your voice is potentially recorded on there. If that's an issue for you, let me know, and we'll arrange for me to turn off my microphone when you're speaking, or you can talk to me through chat or something like that.
I just had a quick question.
Yeah.
Did you say you're sharing your screen? Because I don't see it.
Is anybody seeing my screen?
No.
Oh, thank you, Zoom. Okay. Well, I tried stopping it earlier and it wouldn't stop, so I'm guessing it's not sharing. And this may be a challenge. I may have to kick people out and come back in. Well, but the recording is at least catching my screen.
It doesn't show that it's recording either, and I didn't get a message.
Yeah, I'm not recording through Zoom. I'm
Sweet.
recording on my own. But I don't know how to fix the share. Let's see. So Zoom does this once in a while.
Sharing our screen, and then you could.
Say again?
So maybe one of us could try sharing our screen, and then you could.
Yeah, go for that.
Oh, just kidding, you disabled it.
Okay. All right, well, maybe it's time for our first break, because I may have to close out Zoom, because it does this to me sometimes, and like I say, it's telling me that it's sharing, and it's got a stop share option, but it's not doing anything. Let me... Yeah, all right. I'm going to end the meeting. I'm going to start it right back up. So you'll get kicked out. Just go ahead and hop right back in, and we'll see if that works. Give me about a minute though, because I'm going to shut down Zoom all the way.
Sounds good.
It's working now.
All right, awesomeness, technology. Sometimes it's a good thing. All right, we'll just let people come back in.
Hello.
Hello.
Now see your screen.
All right, so yeah, so I record on my own and I post through YouTube, and there's links to the videos on Canvas, and so those first few minutes when I was kind of poking around the syllabi and stuff, those will all be on the recording, but you didn't actually miss anything critical as far as what I was displaying.
Oh, shoot. Honestly.
And I think we had about 16 people before I ended, so we'll wait a few more minutes.
Is that a drum set?
That is a drum set, yeah, electric drums.
Oh man, that's awesome.
Yeah.
I just got a drum kit like 3 weeks ago.
Oh, cool. Having fun with it?
Oh man, too much.
Yeah.
I have to wait for my parents to leave the house though.
Oh, yeah. Yeah, if I get a house, I'll get a real drum set, but I got electric for now.
I got an electric guitar, just trying to form a band.
Excellent. Man, there are a lot of music people in the program.
You guys have a nice break?
Worked a lot.
All right, so I think we're mostly back. I think we were at 18 before. Cool. So yeah. So the beginning part will still be on the recording. All right. So let's go through the rest of this. So that was the syllabi. Additional course policies. And this is the part that's sort of specific to this section and this quarter. So office hours, again, you can find those through that website. Class meeting time, lab hours, so you can work on lab anytime you want. But again, Tuesday, Wednesday, Thursday, 11 to 12, I'll be online, and I'll be online through this Zoom link, not my office hours link. So basically, just come to class an hour early if you want to find me, or pretend you're coming to class an hour early on Wednesday, and you'll catch me there. Again, I'm recording the lectures and posting those on YouTube. And if you have any concerns about that, let me know, and we'll figure out what makes sense. Homework will be pretty much weekly. It'll be posted on Canvas, and the plan is for you to write it up and then submit it online, and you want to submit it as a PDF file. Okay. And there's some details on Canvas that we'll go through later on. We don't have to do it today, on how I would like your homework written up, as far as how it's organized and so on and so forth. We'll talk about that another day, and also if you need help figuring out how to turn your homework into a PDF, let me know. I don't recommend trying to write your homework in something like Word, right? I recommend writing it on paper and scanning it. And you can scan, with a camera, with a phone camera. You don't have to have a scanner per se. But if you don't know how to turn that into a PDF, we can talk about that. And there's a lot of ways to do that. And it's a good thing to have in your toolkit, right? Being able to make documents and add pictures to them and stuff like that. I don't grade for attendance, but you really want to come to every class as much as possible. Okay, there's only 20 class sections in the quarter. One of them goes to the midterm, right? So each class, is more than 5% of the course. And everything builds on everything else. So missing one class is pretty hard to recover from. If you go home and if you're home, if you watch the videos and you do the work and you come to office hours and ask your questions, before the next class, you'll probably be okay. But if you just miss a class and you don't do anything to make up what you might have missed, you're going to start falling behind, right? Because the next class's material will not make as much sense. So try to plan on coming to every class. Labs, again, you do them online. They'll be posted each week, and we'll go through Lab 1 in detail today. And then your submission for each lab is a lab report. And this is a formal report, and it's got to be written as a formal report. It's not a homework set. It's not, one sheet of paper where you just write down the answers to each question. And lab reports I would like produced on a computer. Okay, I want that to be, a typed document, basically. And we'll go through detailed lab report requirements later. But this is really what's used to give you a grade for the lab. So this is the presentation of the work you did and the results that you found and your conclusions and all of that stuff. Okay. So we'll talk about that in more detail in a little bit. Individual work we talked about. Late work. So I don't accept late work. Okay, the deadlines are pretty rigid. That's really important, one, to keep you on track with the material, two, because, if homework is due at 12 o'clock, chances are by 12:05 we're going to be talking about the homework in class, answering questions people had and so on. And then if you turn in the homework at 12:30, well, that's not really fair to other people. So all the deadlines are rigid except for labs. Labs can be turned in late, but it's a pretty steep penalty for each day it's late. It's 20 points. Okay, so but it's also absolutely imperative that you do the labs. The labs are one of the key ways that you learn the material. So plan on getting the labs done on time as much as possible. And in general, you know, for not just this course, but any course, after you've turned stuff in, check your grades in Canvas, right? When you get an assignment back, double check Canvas, just make sure you're getting the points that you want. At the very least, make sure you keep all of your work so that, you know, if there's some dispute later, you know, you still have a copy of your graded assignment. That's not as much of an issue since we're online anyway, because everything's being done electronically. But, you know, if you're getting things graded and handed back to you on paper, that becomes a bigger concern. All right, Zoom notes, I don't think we need to get too worried about. Da. Yeah, okay, so this was mainly for people getting started on this. And a little bit of wordage here about making PDF files, but like I say, we'll talk about this in more detail. But basically it just points to things like the snipping tool or IrfanView for Windows, and snapshots for Linux and so on. So you can look through that at your leisure. And the rest of this is just links to video information. So you can click through to the actual lecture videos here. It's just a playlist on YouTube. And this also includes my CS classes. So they'll be mixed in together here, but Engineering 250 will pop up. And I also index the videos, so you can click through to a list of topics, and that's useful sometimes for searching. More for CS just because there's so many classes and it's a year-long sequence, but I'll put stuff in here for Engineering 250 also, and you can search this page and so on. It seems to be a useful resource, but again, I'll ask you not to rely on the videos in place of coming to class, because it's really not the same thing. All right, any questions about any of that stuff? All right, so let's talk about Lab 1. And then let's play around with Tinkercad a little bit. And I'm just going to...
Are we going to do all of our circuits in Tinkercad, or are we going to use other software too?
We're pretty much sticking with Tinkercad as far as I know right now. When we get to Engineering 270, we'll use different software if you're doing that in the summer when it's still online. But yeah, Tinkercad's pretty much it for 250. All right, so let me just bring up my own copy of this. All right, so Lab 1 is kind of a hello world for digital logic. So it's playing with Tinkercad, it's getting familiar with the test equipment and some of the basic components and so on. So preparation, there's some reading you can do from the book, some videos you can watch on different types of lab equipment and so on. Izad made these videos, they're pretty good. And then we have a series of experiments. Okay, so experiment 1, introduction to the instruments. So here we're learning about some of the basic components and test equipment available. So for each of the following instruments in Tinkercad, describe the parameters that you can change and its associated range. All right, so let's mess around with this a little bit. All right, so if you've done 120, presumably you have a Tinkercad account, but if not, go ahead and go to tinkercad.com and sign up for an account, or you can log in through Google and they don't spam you and things like that. So you get to a page like this. Okay, this is your basic home page. Come over here on the left, go down to circuits. and it'll give you options for, it'll show you the circuits you've already created. So we're going to create a new circuit.
Do you have a link that will connect your class to our Tinkercad?
I do not. I haven't played around with that because I think it's a relatively new option.
I have a question.
Yeah.
In Mr. Teicher's 120 class,
Mhm.
we use Tinkercad accounts, but I'm not sure if they work for this class. I thought they were class specific. If you still have an account?
Yeah, give it a try, and if it doesn't work, just come up here. Well, let me hop out of here. Actually, I'll tell you what.
I think that's class specific because you need a code to enter in. I don't remember what it was.
Okay, so so hop into Tinkercad, log out if you're logged in, and just do join now, and create a personal account, and you can either sign up with email, or if you have a Gmail account, you just log in through that. But if not, just give them an email address, date of birth, so they know that you're over 12, I think. Pick a username and password, and you're good to go. Make sense? And you want to have your own Tinkercad account anyway, because it's cool software, and there's good stuff you can do with it. All right, so let's create a new circuit, and over here on components, change that from basic to all. You're going to want to do that for pretty much everything we do. And so, you've seen this before. There's components up here, resistors, capacitors, LEDs, switches, and so on. And then there's test equipment. A power supply, multimeter, function generator, and oscilloscope. And I'm just going to drag some of those in right now, just so that I have them. And let's just go up here and pull in, I don't know. We'll pull in a resistor. And let's grab a breadboard while we're here. And hopefully, when you've seen this before, you got the idea that this is really more fun to just kind of experiment with than to try to read in tutorials and things like that. Just experiment. It's pretty forgiving. All right, so for each of these, describe the parameters that you can change in its associated range. Okay, so let's look at a resistor, right? So I'll just click on the resistor, and really your only option is resistance, right? So I can specify how many ohms or whatever units I want. So I can do pico ohms, nano ohms, micro ohms, all the way up to giga ohms. So bang, there's a 1 giga ohm resistor. So look at that range and think about what it means and describe the options for that. LEDs. Not a whole lot of options, pretty much just color. But you can click on that and see what the color options are, and so on. So for the components, pretty straightforward. For things like the power supply, well, click on that. So we've got some options. We can set the voltage, we can set the current. But if we're actually running a simulation, and you zoom in on here, you've got some other options, right? So hold on. Yeah, you get a little laggy with zoom going. So there's a knob for adjusting voltage. And here's a knob for adjusting current, but it doesn't seem to do anything, right? Our current is always 0, so what's going on with that? Well, experiment with it and see if you can figure that out, right? There's a power button for turning the whole thing off or on, and there's 2 connection points here. Well, that's your output, right? So this is your negative output, this is your positive output. So you could write that up for your voltage and so on. Okay, so that's basically experiment 1. Let's see. Hold on. Hold on 1 second. All right, so power supply is same from 120. It just supplies voltage. And multimeter you used in 120 also, so you can measure voltage or current or resistance. The function generator is probably new this quarter though. And the basic idea of a function generator is to be able to generate a signal. Now, a power supply generates a voltage, which is a signal, but it never changes. But a function generator will generate a signal that changes over time. And there's a few different types of signals we like to generate. A square wave, which just alternates between high and low. So it might go, 5 volts for a while, and then 3 volts, and then 5 volts and 3 volts. A sine wave looks like a sine wave, so it smoothly changes between 2 voltages. And a sawtooth wave linearly grows from 1 voltage to a higher voltage and then linearly drops to the lower voltage and goes back and forth. So this will generate these oscillating waveforms, right, with different shapes. And when you have an oscillating waveform, there's some parameters you can specify. So we're going to draw a lot of pictures that look like this. A graph where we have time on one axis and we have, for example, voltage on another axis. And a sine wave, well, it looks like a sine wave. If you've done trig, if you haven't done trig, it still looks like a sine wave, but that won't mean as much. But it changes smoothly, right? Say between, 2 volts and -3 volts. And a square wave, might do something like this. But even for the same shape, we can have different waveforms. Right? So a sine wave could also look like this. It could go up and down a lot more in a certain period of time. Or it could look like this. It might be going up and down very slowly. So there's these different parameters related to waveform signals that change over time. And these are mostly frequency, amplitude, and phase. Okay, and we don't need to worry about these too much. If you're electrical engineering and you go on to like engineering 204, we'll get into these in more detail. Mostly we worry about frequency. Frequency is how fast something is changing up and down. So this waveform that's going up and down really fast, that's a high frequency. And the frequency is really how many times does it go up and down, usually per second. This is a lower frequency, this is a very low frequency. When you talk about sound and you talk about, a 60 hertz tone, which is that hum you get when you have something not grounded correctly, that 60 hertz means 60 times a second there's something moving up and down, right? In this case, it's your eardrum. When you have a 4 kilohertz signal, 4,000 hertz or 4,000 oscillations per second, that's a much higher tone. So we can control the frequency of a signal generated from here. Right now it's set to 1 kilohertz. Kilo is 1,000. So that's 1,000 times per second it'll go up and down. We can also control the voltage level, right? What voltage will it go between? Well, it typically goes between 0 and some number of volts, in this case 5 volts. But we can adjust that. And we can also offset this. So this is called a DC bias or an offset. And it says, you know, instead of going between 0 and 5 volts, let's move everything up 2.5 volts. So you want to explore this function generator and you know, see what these different knobs do and what happens when you change the frequency and so on and so forth. All right. One way to do that is to use an oscilloscope. And so these videos that are mentioned up here, right, this is a good one to look at to get a rehash of all of this. But basically, the oscilloscope is a way to look at a signal that's changing in time. Now, if you have a multimeter, you can measure a voltage, right? And so, for example, I can take this multimeter and I can connect a wire up to my power supply. And I can run this, and I can put this on volts. And, you know, whatever I dial in here, I can see the voltage. I'm getting a negative voltage. Why am I getting a negative voltage?
You have the wiring backwards?
Yeah, I have the wiring backwards. I hooked up the red one to ground, and I hooked the ground up to the positive. So it thinks it's a negative voltage. Plus minus on voltage is arbitrary, but it's standardized. But there's nothing inherently negative about electrons or positive about protons. So I can use a multimeter to measure a voltage, but if I try to measure a signal that's changing over time, that's not going to work very well. So if I hook this up like this, and I run this, well, it's telling me I'm getting 2.48 volts coming out. Well, that's kind of a weird thing. If I set this down to change 2 times per second, you can see what's happening. My voltage is changing between, you know, a few millivolts and 4 point some volts. And there, you know, it's changing once a second. It toggles between high and low, and you can kind of see that that's what's happening here. But it's a really inconvenient way to look at this waveform. So the oscilloscope is a nice way to get a view of what's going on. So let's hook these together. And all of this, you know, you don't want to be like taking my word for this. You want to just get in there and start playing with this. All right, so I'm generating supposedly a square wave at 1,000 cycles per second, and this is the picture I'm getting out, right? Now, what I'd like to see is something like this. Right, something that moves up and down over time. And I'm not really getting that. I'm just getting this, like, you know, something low and then it goes up and it's something high. So how do we look at a signal that's changing in time on a display like this? Well, we basically imagine that you take a pen and you start drawing on a piece of graph paper. And as you're drawing, you check to see what your input voltage is. And if it's 0 volts, you're drawing right here. If it's 5 volts, we're going to draw up here. If it's 2.5 volts, we're going to draw right here in the middle. And we're going to move our pen at a fixed speed from left to right. And at each moment, we're going to move it up and down based on what the input voltage is. And then when we get all the way to the right, we're going to come back to the left and we're going to do it again. And we're just going to keep doing that. Well, now we're doing the job of an oscilloscope. But you can imagine that depending on how quickly we move this pen across the piece of paper, we're going to see different things on our graph. If we move the pen very fast, the input might not change by the time we go from the left to the right. Whereas if we move the pen very slowly, we might move it this far and then find that the input goes up, and we move a little further and we find the input goes down. We might actually see something that looks more like, a waveform we're expecting to see. So we can change how quickly that pen moves across. If we click on this, there's a setting time per division. So a division is the distance from one line to another, and it says how long would we like to take to draw from this point to that point. And right now it's set to 100 milliseconds. Alright, well, let's do some math. If this is going up and down 1,000 times per second, remember 1 second is 1,000 milliseconds, which means in 1,000 milliseconds this has gone up and down 1,000 times. And so if you do 1,000 oscillations in 1,000 milliseconds, it might make sense that one oscillation takes 1 millisecond. So in 1 millisecond, a thousandth of a second, we expect this wave to be high and then low and then go high again. Well, we've got 100 milliseconds from one line to another. So let's change that. Let's make that 1 millisecond. Well, that wasn't what I...
Frequency is 1 hertz right now.
Ah, you're right. Okay. Well, thank you. Alright, let me go back to 1 kilohertz. Let me just click on it. Alright, so we're back to 1 kilohertz, and this was originally 100 milliseconds. Alright, so you may remember Tinkercad sometimes gets a little slow. You can get confused on things. Alright, so we're doing 100 milliseconds per division. Let's change that to 1. And so now we're seeing something more like what we were expecting. The distance from here to here is 1 millisecond, and in that time our waveform is high and then it goes low. And then it goes high again and low again. So now we can actually see, something like what we were expecting. And now if we just change the function to a sine wave, there's a sine wave looking thing. And if we change it to a sawtooth, there's a sawtooth. And if I change this to something else, like if I say, for example, that I only want to go half a millisecond per division, well, what is that going to do?
You gotta restart the simulation.
I'm going to be stubborn for...
Change the time per division.
I'm going to be stubborn for a second and see if I can trick it into doing it.
Why I don't want to think about it.
Because it's actually kind of hung up right now because I just changed to a square wave. Alright, we'll stop and restart. Okay, so now the time to go high and low and then back high again is taking 2 divisions. Alright, you can somewhat sometimes change this while it's still running. But there's some things that you change that it seems to get brain locked on. Alright, so now I'm doing 1/4 of a millisecond per division, and you can see it takes 4 divisions, 1, 2, 3, 4, to do a complete cycle, high and then low again. right? Now changing this, the settings on the oscilloscope, does not change the signal, right? The signal is being generated by this function generator. That's not changing. What I'm doing is I'm changing how I'm looking at the signal. So I'm moving the pen more slowly across the page, or more quickly across the page, so that my pen gets further before the voltage changes. All right. So make sure you think about that, right? The difference between the function generator, which is making a signal, and the oscilloscope, which is displaying it. And they're totally separate functions. All right. And once you have a hookup like this, you can use the oscilloscope to understand the function generator a little better. For example, this DC bias knob, if I move this, you can see what happens. The picture of the waveform moves up and down. If I change the amplitude, it shrinks, right? But it still stays centered at the same place. So those are the things you want to do for experiment 1, right? It's called an experiment instead of a homework question because we're not telling you exactly what to do. And there's no single correct answer for what you should observe, right? The goal is to you know, imagine you're in a lab and you have this equipment and you put it together to build test circuits and you explore some aspect of the subject. In this case, you're actually exploring the test equipment itself.
I have a quick question.
Sure.
What does it mean by associated range?
Oh, so for example, like for the resistor, the only thing you can change is the resistance. But what's the largest and smallest resistance that you can specify? So that would be the range of the resistor. For a power supply, there's multiple things that you can adjust. For the function generator, there's even more things that you can adjust. So in addition to saying I can change the waveform, I can change the frequency, I can change the voltage, right? Try to specify some of the other information about those parameters. I can change the frequency from this to that. I can change the voltage from this to that, and so on. So you're just looking to explore, you know, different aspects of the equipment. Make sense?
Yeah.
Okay, cool. All right, so that's experiment 1. Experiment 2, this is a repeat of an experiment from 120. You have a proto board in Tinkercad as well, and you just want to sort of figure out what the connectivity is. So you probably already remember this, but you know, you can take your proto board and you can take a multimeter and you can measure resistance between different points, although if you just point on this, it kind of tells you the answer of what's connected to what, which is, you know, all of these holes are connected to each other, and all of these holes going across are connected to each other. But you can, you know, pop the leads from the multimeter, set it to resistance, plug that into a few of these, and just get a feeling for how you can use the multimeter to measure, you know, connectivity between different points. And that's probably the thing that people do most with multimeters, right? I have a cheap little multimeter that I use all the time just to see if 2 points are connected to each other in circuits. It's kind of like, you know, when a doctor listens to your heart, an engineer checks connectivity between points in a circuit. It's the first order thing you can go to get a high level view of what's going on in a circuit or a system. All right, so figure out the connectivity between these and put a picture of this in your report and draw lines to show what's connected to what. And then experiment 3 is a formal version of what we just did in Tinkercad, which is connect the function generator to the oscilloscope and set the generator to make a 1 kilohertz signal, 50% duty cycle, 5 volt, peak to peak, bias of 2.5 volts, and that's pretty much the default setting you get when you first drag an oscilloscope in, or a frequency generator in. Hook that up to an oscilloscope and observe the waveform. So tweak the settings on the oscilloscope to be able to see the waveform going up and down. And then draw a picture of that, right, and put that in your lab report. And then do the same thing with the function generator at 20 hertz, 20 cycles per second. And then do the same thing with 50 kilohertz, so 50,000 cycles per second. And for this one, set a DC bias of 2 volts with a peak-to-peak amplitude of 4. For this one, peak-to-peak amplitude of 3. So, again, peak-to-peak amplitude is the voltage difference between, say, here and here. The top part of the waveform to the bottom part. That's the peak-to-peak voltage. Normally, we think of a waveform as being centered around an axis, but we can slide it up or down. That's what the DC bias is. So if you were to add 1 volt, let's say this was 2 volts and this was minus 2 volts. If you were to add 1 volt everywhere, then this would be up at 3 volts and this would be down at -1. And your waveform would look something like this. So experiment 3 is just playing around with those concepts. All right, experiment 4 we're going to come back to. We're going to do like a 4-minute break, and then we'll come back, and I want to talk about lab reports in general, and then I want to start talking about some of the subject matter of 250, and then we'll loop back and touch base on experiment 4 at the end of all that. So let's take about a 4-minute break. And we'll meet back here at 1 o'clock and continue talking about labs and lab reports. All right, cool. We're back. All right. Any questions so far about the lab? All right. Let me talk a little bit about details of lab reports. So there's this guide to writing lab reports that I posted on Canvas, and there's a lot of wordage in here. It kind of grows over time, but let me tell you the punchline about lab reports for me. You know, the scientific method, right, is basically about trying to verify or refute certain ideas. So you have a theory about something and you construct an experiment to test that theory. And you make observations and then you analyze those findings, and it may support your theory or it may contradict your theory. Okay, this is how science is done. Your lab report is a presentation of what you did, right? To some degree, why you did it, how you did it, what you observed, and what you concluded. And the mindset you want for lab reports is, imagine that you're trying to share what you've done with somebody who's not in the class, has never taken Engineering 250, but has the same basic background as you. So somebody who's, you know, done some electric circuits in Engineering 120, CSE 120, but has not done these particular experiments, right? You need to describe in your lab report what you did, how you did it, what you observed, and so on and so forth. So your lab report needs to stand on its own. You can't hand somebody the lab report and say, oh yeah, take a look on Canvas to see what I did. Okay? It should stand completely by itself. So if you're using a circuit and you're taking measurements of that circuit, your report has to include a picture of that circuit, right? Typically a circuit diagram. If you're asked to, you know, make recordings of the voltage across this piece of a circuit as you change the voltage from this to that, you can't just list a bunch of numbers in your lab report. You have to say, in this experiment, I changed the voltage from this to that and recorded the voltage across this component. Here's a table showing what I observed. Okay, so that's the punchline of what should be in a lab report, and that's what all of this stuff is here down at the end. The beginning stuff is just basically like general guidelines for pretty much anything that you're producing and turning in online. So I want your labs to be typed. Okay, homeworks can be handwritten. Labs, I'd like them to be typed, right, meaning computer generated, except for circuit diagrams. You know, if you have pictures of waveforms like we've been drawing, things like that, you can draw those neatly and then scan them or photograph them and put them into your document. Okay, your labs have to be submitted as a PDF, and if you're using Word or LibreOffice or anything like that, Google Documents, you can always export or save as a PDF. Okay.
A question about the like a waveform.
Sure. Mm-hmm.
Would you accept, you know, taking like a snippet of the oscilloscope?
Yeah, unless it asks you to draw it. And I think in Lab 1 it asks you to draw it.
Okay.
But in general, you know, if you're looking at a waveform, yeah, you can take a screenshot from the oscilloscope. Or if you're in an actual lab, you know, you can take a picture of the waveform on the oscilloscope screen. That's all fine.
Okay.
Cool.
Can I draw in MS Paint?
Say again?
Can I draw in MS Paint?
Yeah, you can draw on Paint. Whatever works for you. Don't undervalue, though, the possibility of drawing by hand and taking pictures, because unless you really are comfortable with using, you know, automated tools for making pictures and stuff, a lot of times it's a lot easier and quicker to draw by hand. But if you have a tablet or something, that can be nice. So reports are written individually. We're not working in groups, but if we were working in face to face with lab partners, you'd still want to do your own individual report. And everything in the report should be yours. Your name is going on the front of the report, which means you're saying everything you find in here is my work. And if there's something in there that's not your work, you have to make that clear. For example, if you were to take a picture from the lab assignment of a circuit and then copy and paste that into your report, that's okay, but you've got to mention in there, this was taken from such and such a source, right? Otherwise, you're claiming that it's yours, and if it's not, that's technically plagiarism. Okay, so you want to get good at citing sources. And, that's a common thing to do when you write a technical paper. Not everything is going to be original, and you don't need to reinvent the wheel. You just need to give credit, right? You need to say, this is coming from, the ENGR250 text, which I got from this place, or something like that. Formatting, I'm not super picky about formatting, but I want a cover page which says ENGR250, the number of the lab, and your full name, which is first name followed by last name. Okay? Try to avoid using initials. Try to avoid just using your last name. There's a lot of people with similar or identical last names, people with the same initials, and so on. If you had lab partners, you would say lab partners and list the full name of your lab partners. But we don't have lab partners here. And then the date on which you wrote the report. Okay, that goes on a cover page. That's the only thing you find on the cover page. And then basically, I just want this organized into sections, right? Starting with an introduction, which tells me, what is this report about? In this lab, we worked with Tinkercad, and we got familiar with test equipment, and designed some circuits or whatever, right? So kind of a general introduction to the whole report, and then you can start talking about each experiment. So make a section called Experiment 1, and just, depending on the experiment, the specifics will change, but generally you're going to have some kind of, overview of the experiment, objective theory. I don't actually remember putting these in. I'm not going to be super concerned about having sections with these particular names, okay? Take these as suggestions. But I want a separate section for Experiment 1, another section for Experiment 2, another section for Experiment 3, and so on. So make sure your experiments are clear, and make sure that these things are included, whatever you call them. But let me know what's going on in each of these experiments, right? What are you doing? How did you do it? What did you observe? And what do you conclude from that? Okay, now some of this, doesn't apply a whole lot in Lab 1 because we're not really, discovering the oscilloscope or something, but in some sense we are. And then after you've done all of your sections on experiments, I want a section called Conclusions and Lessons Learned, and this wraps up everything. This is the counterpoint to the introduction, right? So these are not random experiments usually. There's some connection between them. So what did you learn? What did you conclude from this? Okay, and then there's a final section called New Experiment. And here you want to think of, if you're doing 4 experiments in this lab, come up with an Experiment 5. Okay, something that's not, one of the experiments you already did, but something that, would continue the lab into a 5th experiment. And this can be hard, okay? This takes some thinking. But spend some time on this, figure out a new Experiment 5 in this case, and then describe that experiment. So Experiment 5, we're going to, such and such, and then do that experiment. Okay? All right, does that make sense?
So far.
Okay. So that's just a general guideline. What I don't want to see is a piece of paper with a bunch of numbers written on it, and that gets submitted as a PDF. Okay. For homework, you say 1 period and you list the answers to question 1, and 2 period you list the answers to question 2, and so on. Right. Lab report is different from a homework. It's a document that you could hand to somebody who doesn't know anything about this class, and they could still know what you did, and they could reproduce your work. They'd know exactly what circuit to build, how to set the test equipment, what to take measurements of, and so on and so forth. Right? Because this is the other part of science. After you've produced this report, you put it out in the public domain, and other people take it and they try to do the same thing that you did. And if everybody can do this and get the same results, that's more support of whatever theory you were exploring. But if somebody in Zurich follows your steps and they get a different answer, well, now there's something missing from the theory, right? Or maybe they did the experiment wrong. But if, 10 people follow your procedure and get a different answer, now there's something else going on, right? And maybe those 10 people had something in common to how they did the experiment. They did it at a certain time of day and got a different result. And that expands the theory. So this is a version of, how science is done, how our body of knowledge grows over time in scientific matters. So it's not entirely artificial. All right, so let's talk about some of the concepts in this course, and then we'll come back and we'll try to talk about Experiment 4. Experiment 4 is a little more involved, and I'll try to get to it before we're done today. We've got about 40 minutes, and if not, we'll come to it next time. So digital logic, right? So what's the difference between digital and non-digital, and what's an example of non-digital? What does digital even mean?
Well, potentiometer is an analog.
Okay, potentiometer is analog. That's cool. Do we encounter potentiometers outside of the lab?
Well, yeah. I mean, especially for music, that's what your volume knobs and stuff.
Yeah. So classic use of a potentiometer, a volume knob, right? And what does a volume knob do? You turn it and it makes things louder or softer, right? Now I have a volume.
The flow of electricity.
Yeah, it changes the flow of electricity. And on my little music player, right? I have the standard $20 music player everybody has from Amazon. I don't have a knob for volume. I have a pair of buttons, and one button makes it louder and one button makes it softer. Now my volume knob I can turn, and it's a pretty smooth change in volume as I turn it. My buttons that I click to make the volume louder or softer, it's not a subtle change. It jumps up from soft to a little louder, back down to a little softer, right? And this is the nature of digital versus analog. So there's a dual concept here. Analog tends to be continuous. Things move smoothly. Digital is what we would call discrete. Things move in jumps from one voltage, one volume to the next, to the next, to the next. Analog changes smoothly. So if we look at the voltage coming out of a device, we measure it with a multimeter. If it's an analog signal that's coming out, it might, change something like this. Where again, this is time and this is voltage. But a digital circuit, if I were to measure the voltage, it might do something like this. I would see one of two voltages coming out, for example, either 0 volts or 5 volts. Whereas here, I'd see 0 and, 0.23 and 0.56 and then, 0.4 and then 1.3 and so on, and it changes smoothly. Unfortunately, this is what our music is today. that's a whole nother topic. Because this, can be used to approximate that, right? I could simply say anything that's, above this line, I'm going to represent that as something high, and anything that's below that line, I'm going to represent it as something low. And hey, there's an approximation to that waveform. Now, that's not a very good approximation, but it's an approximation, It certainly distinguishes that waveform from, this waveform. And even with a digital signal, we can make a better approximation, because here we're only going between two values, like low and high. But we could have, 4 values. We could have low, pretty low, kind of high, and very high. And we could get a better approximation to this. So these are kind of endpoints, right? This is a continuous, totally analog signal. This is a very discrete signal with just 2 voltage levels. But there's ranges in between here. And so we can digitize, right? Take an analog signal and turn it into some kind of digital waveform. But we can do it with varying degrees of precision. All right, so we'll talk more about that another time. But let's just think about this extreme. Let's just think about a pure digital world where everything is either high or low. All right, so we're taking the world of engineering, computer science 120, where we had circuits and we had to do, dare I say it, KVL, KCL, and Ohm's law and all of that sort of stuff, and measure voltages and calculate currents and say, the current here is 2.3 milliamps and the voltage is 5.16 volts and so on. And we're getting rid of all of that. And we're moving to a much simpler world. Yeah. And in this simpler world, we have 2 things. We have basically high and low. And if we're looking at voltages in a circuit, we're going to deal with circuits where we only have 2 voltages, typically 5 volts and 0 volts. And that's it. And when we do our calculations and we make our measurements, we're just trying to answer the question, is the voltage 5 volts or 0 volts? It's a much simpler life. We sometimes call this true and false, or we might call it on and off, or we might call this a 1 or a 0. Or, we might call this false and true. Nothing wrong with that. But the punchline is we've split our world into 2 things, right? What we call them is kind of irrelevant. But things are either this or that. Okay? That's binary. Right? Binary 2. So digital logic, binary logic, kind of the same thing. This is also called Boolean logic. So why is it named Boolean? Where does that term come from? Was that a question?
That was my question, because I work in software and I was introduced to the term Boolean.
Yeah, it's a type of variable. So yeah, anybody know the name Boolean?
Binary operation something. I forget the other 2 letters.
Mm-hmm. So this is actually someone's name. This was actually George Boole, who was a mathematician. And he was doing his thing in the mid-1800s. So a long time ago. Boolean logic is over 100 years old. So people were studying this long before we had transistors or electric circuits. that we could use to do the kinds of things we're doing in this course. It was a branch of mathematics. And Boolean algebra, which we'll be using, is a branch of mathematics that George Boole explored. And this was used, you know, in the 1800s to try to understand thought, to try to understand how our minds work. Not the mechanics of you know, neural pathways, but the logical processing that we do, the way that we analyze things and come to conclusions. Well, people have wanted to understand this forever. And a lot of the work, you know, early Boolean algebra and stuff went into, you know, coming up with theories and trying to understand how we process information. And all of that was sort of sitting there available when we started building electronic computers, you know, in the early part of last century. We had all of this foundation to build on. So this is called Boolean algebra, Boolean logic, and so on and so forth. And in most programming languages, there's types of variables. A common type is a bool, right, or a Boolean, and it's a value that, guess what, it can take on one of two values, usually called true or false. All right, so we've got the simplified world where we have two things, and this kind of begs the question. Right, which is, what can you do if you only have two things? Boolean algebra, right, is the thing. Well, we know about algebra, right? You can add, subtract. There's variables and equations and picture problems and all kinds of stuff. And algebra that we talk about in school usually deals with numbers. And, you know, numbers can be positive, negative, zero. They can be fractions. They can be weird things like pi and stuff like that. Boolean algebra is the same kind of thing, but your universe of objects is just 0 and 1. And so if the whole universe consists of only two things, a 0 and a 1, right, what can we say about, you know, doing things with those objects? What could we possibly do? Well, there's Boolean operations, and they're similar to doing things like addition and subtraction and multiplication, but on this much smaller set of objects. So let's look at some of these Boolean operations. And so you know, our universe consists of a 0 and 1. Well, here's a really simple Boolean operation, not, right? Or sometimes called inverse. And if we take the inverse of 0, we get 1. And if we take the inverse of 1, we get 0. Is that useful? I don't know, but it's something we can do, right? We're trying to build up, you know, some fancy sounding algebra of operations we can do on zeros and ones. Well, there's one thing we can do. We can turn a 0 into a 1 and a 1 back into a 0. Another thing we can do is what's called an AND. And an AND operation takes two arguments and tells us if the first one is a 1 and the second one is a 1. So if we do an AND of a 0 and a 0, we'll get a 0. If we do an AND of a 0 and a 1, we'll get a 0. AND of a 1 and a 0 will give us a 0. But if we do an AND of a 1 and a 1, we'll get a 1. So this is an operation that takes two arguments and tells us if the first one is a 1 and the second one is also a 1.
Wouldn't the 0 and the 0 be a 1?
Well, so the question is this a 1 and is that a 1? Well, that's not a 1. That's not a 1 either. But there are questions we could ask where the answer to that would be a 1. But, you know, these are just, you know, essentially arbitrary functions. We could define, you know, a new function called x that looks like this. That's a perfectly good function too. That's actually something called an exclusive NOR, and we'll use that a lot in a few weeks. All right, here's a function called an OR. And an OR answers the question, is this first argument a 1 or is the second argument a 1? Well, in this case, that's not a 1, that's not a 1, so neither of them is a 1. But in this case, yeah, the second argument is a 1. And the OR function will be equal to 1 if either the first argument is a 1 or the second argument is a 1 or both. Right? Because if they're both a 1, then that first argument is certainly a 1. So this is what the OR function does. And I did something when I started writing this out. I wrote this out first, and then I wrote that. And this and this and this all kind of look the same, right? It's a different type of function name, but then it's parentheses, and there's a 0, 0, 0, 1, 1, 0, 1, 1. And the only thing I had to change was this part over here. So we'd like a way to be able to describe what one of these Boolean operations does to its inputs, so we can describe what is an AND, what is an OR, what is an X, right? And this works, but there's a more standardized way to do this, and that's to use what's called a truth table. And a truth table, it's kind of like, you know, a multiplication table that we use in school, but a slightly different form. So truth table looks like this, and I know a lot of this is rehashed from 120, but we're going to build on it. So I might list A and B as two inputs, and the trick is to list all possible combinations of A and B. And then I can say, okay, if this is what A and B are, what does the AND of A and B look like? And I could say, well, you know, 0 and 0 is 0, 0 and 1, 1 and 0 are 0, but 1 and 1 is equal to 1. Well, that's a truth table for the AND function. And the AND we abbreviate as A period B, or sometimes just AB. And is that a totally random choice? Writing down something that looks like A times B when we mean AND?
No, because if you multiply by 0, it get 0, right?
Yeah, this actually looks like multiplication. 0 times 0, 0 times 1, 1 times 0 or 0. 1 times 1 is 1. It is multiplication. And so an AND is sometimes called a product. We could say the product of A and B. We could say A and B. All right, and so for an OR, we saw that our values look like this. So this is the truth table for an OR. And an OR we write with a plus sign. And we actually use the word sum to mean an OR. Well, that's a little bit of a stretch, right? So 0 plus 0 is 0, that's good. 0 plus 1 is 1. 1 plus 0 is 1. It kind of breaks down here. 1 plus 1 is not 1. 1 plus 1 is 2, right? And 2 is not a Boolean thing. So it's not exactly addition in the usual sense. But in a mathematical sense, yeah, it actually is exactly addition. But regardless, that's the truth table for an OR. And so we can define, you know, all kinds of operations, and we'll do more of this later, but let me show you one more. This is something called a NAND. And this is written as AB with a bar on top. And a NAND is a not AND. So the way that I think of a NAND is I do an AND, but then I take the inverse. And so I can just look at the values of an AND and just write down the opposite value. That gives me my truth table for a NAND. And same thing for a NOR. A plus B with a bar on top. Well, it's going to be exactly what I got for an OR, but I'm going to replace zeros with ones and ones with zeros. So there's the truth table for a NOR. So we'll go into more of this. We'll look at exclusive ORs and inputs of more than two variables and so on and so forth. But this is the basic notion of a truth table, right? Basically, if you have a function with a certain set of inputs, we list all the possible combinations of those inputs, and for each combination, we just list the value of the function for that combination. And once we've done that, we know exactly what this does for any input combination. What's the AND of 0, 1? Well, I'll just look at 0, 1. The AND is a 0. Okay, so why do we care about this? Because we can use truth tables to describe a circuit that we're interested in building or analyzing. And this is where we're going to go with experiment 4 in lab 1. And this is still mostly rehash of 120, but I want to do this in a very particular way. So, so let's design a simple circuit. Okay, let's make a circuit for a combination lock. And this combination lock is going to have 3 buttons. And the way we're going to set this up is if you press a button, that's going to generate a signal that we'll call logic value 0. And if you have a not pressed button, that's going to be a logic signal 1, right? And again, that's pretty arbitrary. We can use whatever names we want for high and low, right? It's just 2 bins. So I'm just going to use this numbering convention that when I press a button, it's a 0. When I don't press it, it's a 1. And here's what I'm going to do. I'm going to have 3 buttons, A, B, C. And I have 8 possibilities. Right? In this case, none of my buttons are pressed. In this case, all of my buttons are pressed. Here I've only pressed the A button. Here I've only pressed the C button, and so on. And I'm going to have an output X. And my output's going to be the following. If this circuit's output's a 1, it's going to unlock a cookie jar, right? And if it's 0, then the cookie jar is going to be locked. So we want to design a circuit so that when the person holds down the right combination of buttons, the system will unlock. And if they hold down an incorrect combination of buttons, the system will be locked. Okay, and let's start off with a secret password. Okay, so so my combination, my secret combination will be 111. Okay, well that's a really goofy secret combination because it means by default if I don't press any buttons, the system's unlocked, right? But I'm trying to be clever because if somebody's going to break into my safe, right, they're going to start pushing buttons and, you know, any buttons they push, the system's going to be locked. The secret to getting in is you don't press any buttons. So this will outsmart the people trying to steal my stuff. All right, so I want to build a circuit that does the following. It's going to look like this. Here's my 40,000 foot view. I'm going to have 3 inputs, A, B, C. I'm going to have an output X. Okay, this is what we call a system diagram. And there's no mention of, you know, what the circuitry is inside here. It's just, you know, this high-level view. 3 things go in, 1 thing comes out. Okay? What I want is when the 3 things going in are 1, I want my output to be a 1. And in all other cases, I want my output to be a 0. All right? That's a truth table that describes this behavior. And this is the first step towards doing circuit design. And pretty quickly in the next few classes, we'll learn how to go from this to a fully functioning circuit that achieves this behavior. But the first step of this, after we know, you know, what we want the system to do, is to make a truth table. And so here's a truth table for a circuit that will unlock when you put in the secret combination 111, which means don't press any buttons. And suppose I wanted 2 secret combinations. Suppose I also wanted to unlock when you typed in you know, a 0, 1, 1. In other words, you pressed button A and you released buttons B and C. And I want that to also unlock my system. Well, the only change I have to make is on that row of my truth table, 0, 1, 1, change X to output a 1. And now this is the truth table for a combination lock that unlocks in response to one of 2 secret combinations, 1, 1, 1 or 0, 1, 1. Is this good so far?
Makes sense to me.
Yep.
Okay, cool. All right, so we'll talk next time about how to go from this to a circuit, but let's hop back to experiment 4 for lab 1. So experiment 4, you're designing a 3-way traffic intersection control signal, a stoplight, right? And you want to set this up as follows, and I'm going to more or less insist that you do it like this. Mainly because if you do it some other way, you're going to be constantly translating from what we talk about in class. So this is west, this is east, and this is south. Now, you know, if you draw it like that and you label it north, south, east, that's still a 3-way intersection. But I'm always going to use this picture. Okay, so this will have better harmony with what we do in class. So that's a 3-way intersection, and you want to conform with the state of laws in the state of Washington for a 3-way intersection, which means if there's more than 1 car present, the car on the right always has priority. All right, and this is a 1-lane road, so we're not going to have cars going, you know, past each other. So it's a simple light that tells each lane whether to go or stop. So we have, you know, a red and a green light on each of these lanes. And so I'll call this, something like west red, west green, south red, south green, east red, east green. And you also have a sensor. So something which tells you whether or not there's a car present. So I'm just going to call my sensors west and south and east. These are car sensors. And these west, south, and east, red and green, these are the lights. All right, so each direction has... Sorry, say again?
For clarification, are those lights, like the west red, west green, are those for the cars on the west-hand side, or for cars going in the direction of west?
Those are for the cars on that lane. So the car sitting here is looking at a red and a green light. The car in the south is looking at red and green, and so on.
Okay.
All right, so each direction has only one lane and one control light, red and green, for each lane. All right, so you want to start doing a design for a circuit to control this traffic light. Okay, so what do you need to do for this part of the design? Identify the input variables into the traffic control system and the output variables to control the signals. So your inputs, you have 3 car sensors, west, south, east. You have 6 outputs, west red, west green, south red, south green, east red, east green. Okay. And how do we indicate that? Well, you draw something like a system diagram. Okay. But make a system diagram for your traffic light controller. It's going to have 3 inputs, 6 outputs. So you draw a rectangle, you draw 9 arrows on it, you label these in a way that matches the labels on your picture, and you put down a description of them. And your description says not just west, south, east is a car sensor, but it also should say 1 means this and 0 means that. And your lights have to say 1 means this and 0 means this. And most people will say, 1 means there's a car present, 0 means there's not. 1 means the light is on, 0 means the light is off. But that does not have to be the way it's done, which means you have to specify how you're doing it. And I recommend doing it that way, but you can do it any way you want, but it's got to be specified. All right, so that's what it means by identifying the input variables and the output variables. Sketch the intersection, so you want your intersection to use the same symbols that you're using in your system diagram. Right? So this is explaining to somebody basically what's the high-level view of your circuit. What goes in, what comes out, and how does that relate to, the sensors and the lights on the intersection. And then you want to make a truth table. Okay, and that's the real deliverable from this experiment is the truth table, because then we're going to use that in lab 2 to start developing a circuit. So what's your truth table going to look like? Well, your truth table is driven by your system diagram. So if you've got west, south, and east are your inputs, and you've got west green and west red and so on, right? For every input, that's going to be a column in your truth table on the input side. And for every output, that's going to be a column on your output side. So in this case, what you should end up with is a truth table with 3 inputs and a total of 6 outputs, which, let me make sure I call them the right thing. Yeah, so west green, west red, south green, south red, east green, east red. So it's a little bit of a big truth table. It's got 3 inputs, it's got 6 outputs. If you have 3 inputs, what are you going to have? You're going to have a total of 8 rows, because your truth table needs to have every possible combination of inputs. And on each of those rows, you should have 6 outputs listed. Okay, that's going to basically give you the truth table for experiment 4. Yeah,
Quick question.
sure.
So let's say there's no cars. Are all lights red then?
Ah, good question. That's up to you. So this is what you want to describe in your lab report, right? When you're doing this experiment, it's up to you. If there's no cars anywhere, you could make all the lights red, or you could pick one lane to be green. And since cars to the right always have priority, if there's a car here and here, east is going to get priority. If there's a car here and here, south is going to get priority. If there's a car here and here, east is still... Sorry?
We're not making an actual circuit out of this, right?
You're not making an actual circuit. It's just a truth table. And so west is lowest priority. And so you might, decide west will be green if there's no cars present. Or you could make everything red. Keep the town calm. But only one light should be green at a time. So if there's a car on west and east, east gets to go, west has to wait. All right, so you decide how you're going to do this, and then you sketch your circuit diagram, draw your system diagram, sketch your intersection, draw your system diagram, and then make a truth table. And the truth table is the real punchline, because once you have a truth table, you don't need to know about this or this anymore. You can hand that truth table to anybody who understands digital logic, and they can build a circuit that will realize that truth table. That's what we're going to do in Lab 2 and other future labs. All right. Yeah.
Are you going to teach us how to make these circuits based off of these tables?
Absolutely. We'll probably start doing that on Thursday. You don't need a circuit for Lab 1, but we'll probably start talking about that on Thursday. And we'll go through the next few weeks. We'll basically be looking at different ways to go from a truth table to a circuit. And that's where it starts to get really fun, I think. All right, so experiment 4, write the truth table, and then this is boilerplate at the end of every lab. So report requirements, clear problem statement, answer experiment questions, schematics, tables, all that other stuff. And then for the whole lab report, cover sheet, which we already talked about, lessons learned at the very end, that's your conclusions and lessons learned, and then a new experiment. All right, and we'll be iterating on this, right? So your first lab report, I'm going to grade very, very gently, right? But I will give you a lot of feedback, like, this should be done this way instead of that way, or you need to have a conclusions section at the end, or things like that. I'll give you heavy feedback and minimal point deductions. And as we move forward through the course, that balance will shift. And you'll start losing more points for things, but you won't be making things that get you point deductions as you move through the course. So it's part of the learning process is figuring out what should go in a lab report, how should this stuff be written up.
Another question.
Yeah.
When we turn in these labs, Jing also had us turn in another sheet that basically was a step-by-step process of like all the moves that you did while you were in Tinkercad. Do you also want us to turn in something like that as well?
No, I'm not going to ask for that.
Okay.
All right, cool. Well, that brings us to 150. So we are out of time here. So if you have questions about this, if you want to talk about Tinkercad or PDFs or any of this material, right, you can come by office hours tomorrow. Regular office hours 8:45, lab hours at 11. Same on Thursday, and you can definitely, absolutely, please ask questions in class on Thursday also. We'll usually start the class period with questions, but that's what really drives the whole course. So don't hesitate. Otherwise, have a fantastic afternoon, and I will see you next time.